The previous video showed an illustrated example of a fictitious force that appears for an accelerated observer positioned at the rear of the cargo box of an accelerating truck. When a ball launcher launches a ball transversal to the truck forward motion, as soon as the ball leaves the launcher it has a forward velocity v1, and since it does not interact with the truck body it maintains this forward velocity v1 constant. Therefore the internal accelerated observer sees the ball moving in a backward curve attributed to a backward force. Since a body cannot manifest a force on itself and move, this force does not exist, therefore is fictitious. An external non-accelerated observer sees the ball moving in a straight path transversal to the forward motion of the truck. Because the ball is not interacting with the truck and moves in accordance with Newton's first law. That video illustrated the path of the ball transversal to the forward motion of the truck. This is the case when the non-accelerated observer has the same forward velocity v1 of the ball. In other words, the non-accelerated observer has the same forward velocity relative to the ball. However, if the non-accelerated observer is at rest relative to the ground and the road, he sees the ball moving along a straight, but diagonal path. This happens because velocity is always relative. A non-accelerated observer has velocity 0 relative to another observer if their velocities are equal. If the velocities are different, the velocity of that observer will be 0 only relative to a third one. A different situation occurs to acceleration because the observer can differentiate acceleration from non-acceleration using an accelerometer. The accelerometer of a non-accelerated observer indicates 0 acceleration, while that of an accelerated observer indicates acceleration. Acceleration implies Newton's third law with its requirements. However, there is an exception, when the observer is in free fall and the accelerometer does not indicate acceleration, because bodies in free fall have equal acceleration rate determined by the mass of the specified large body causing it. In this example the Earth, and his accelerometer shows the same indication as that of the non-accelerated observer. However, the non-accelerated observer can measure the acceleration of the falling body toward the surface of the planet, and deduces Newton's third law is being applied in a force field, in which case the falling body is in interaction with another reference body, in this case the planet. This conclusion is reinforced supposing the non-accelerated observed is at rest relative to the planet, a new reference. However, since the planet and the observer attached to its surface are in orbit around the Sun, they are also in free fall, only at a different acceleration rate. Therefore, the free fall is seen as the acceleration of bodies without forces, caused by a curved spacetime distorted in the presence of large masses. So we ended up with the two theories of gravitation. In small regions of space, classical gravitation theory employing Newton's third law gives accurate results and is simpler. But the general relativity theory, applied to stars, galaxies and very high speeds, that postulates free fall without forces, but due to spacetime curvature in the presence of large masses, gives the best results in the investigation of the universe at large.